Okay, well, so today, inshallah, we will continue discussing the numerical solution of the swing equation. We already discussed the techniques that could be implemented in power system, not only for swing equation, but any ordinary differential equations. We have the simplest one, which is Euler method, and we have a better version of Euler method, and sometimes it's called the second order Runge-Kutta method or modified Euler method, where we can approximate the slope by averaging the value. We can predict the solution, and then we can correct it in 2 steps. Trapezoidal method also can be used. We can approximate, and in the integration, which gives the solution, is simply approximated by the trapezoidal area under the curve, and then we can continue. And the last, which is fourth order Runge-Kutta method, you can have 4 approximations of the slope, and then you can calculate the solution iteratively till the final time that you need. We stopped here how to implement the trapezoidal method, and we already covered the modified Euler method. Trapezoidal method for the swing equation, to solve the swing equation. So this is simply the recursive form of the trapezoidal rule. X at iteration n plus 1 equal to the solution, or x. Now we need x of t, by the way. This is our solution in general. This is the solution, x of t. We need x of t, or specifically in a swing equation, we need delta of t. I don't know why this is. Okay, so this is the solution. This is the solution. Okay, so x, the solution at, I don't know why this pops up every time. I think. Okay. This is the solution at iteration n, and this is the interval delta t, the time step, and this is the function at iteration n plus 1 and function at iteration n. So let us implement this trapezoidal to the swing equation. So the swing equation, I already covered this, but let us go over it quickly. Of course, the second order nonlinear differential equation, we can put it in 2 first order differential equation as such. So this is F1, this is F1, and this is F2. we have two functions here. So we can write f equal to a vector f1, f2, and f1 at iteration n. طبعا all these are constants except the electrical power, which varies with time. So this is BE of n, and this is BE of n plus 1. And for delta also we can write omega. The speed is a function of time. So this is also delta of n and delta of omega of n and omega of n plus 1. So synchronous speed is constant, as we mentioned. So in this case, if we apply the trapezoidal method, so the solution at n plus 1 equal to solution at n plus h over 2 multiplied by all this, which is fn plus 1 plus fn. Of course, if you can add them up, you can get this value. And also for delta, you can have delta n plus 1 equal to delta n plus h over 2 times this. What we need actually, we need delta of t. Of course, we can get the omega and we can substitute here to get delta, or we can write delta of t right away, and we can replace omega of n plus 1 by all these values here, and also omega n can be replaced by, you can have here omega n is the function of omega n minus 1, and you can replace it by in terms of BE and BE of n plus 1 and BE of n minus 1 and so on. By combining, you can write delta n plus 1 equal to delta n plus h times omega n minus omega s, and you can have this. Okay. Generally, the two resulting algebraic equations can be written as omega n plus 1 and delta of n plus 1 equal to this. Here, we can combine this constant, and this is another constant, which depends on the value at n. And this depends on the value at n. Depends on the value at n. So we can separate, it's very simple, just some mathematical manipulation in order to simplify the calculation. And you already have the value of BE of n. This value is calculated, at n, so it's already known. And you can take it outside the constant multiplied by omega s and so on. And this is also omega n, which is known in advance. You are now talking about the next step, not. So the previous step is already calculated. So you can just do some mathematical manipulation in order to simplify the calculation. So alpha and beta here are constants, depends on the calculation at the previous step. Alpha is defined as such and beta is defined as such. This is from the previous cases. So as you can see here, alpha depends on the value at n and beta depends on the value at n. So observe alpha and beta are determined from the previous step. You can simplify as such. Let us take an example and see if we implement modified Euler, trapezoidal, or Runge-Kutta method, how to proceed. So this is the single machine infinite bus, and we have here like a fault that occurs at point A, near to the bus here. Maybe the fault occurs here or so. But to clear the fault, we may trip this line, or the fault is cleared by itself. All the cases that we consider an equal area criteria, we can develop here the swing equation corresponding to the case pre-fault, during the fault, and post-fault. So this is the frequency, this is the inertia. Initially, the machine delivers 0.8 per unit. At steady state, this is equal to electrical power. Usually, we give electrical power. We say the machine delivers at steady state 0.8 per unit, which is equal to B mechanical at steady state. This is the infinite bus voltage, one with angle 0 reference. And this is a generator, XD prime, the internal voltage of the internal impedance of the machine, and the X of the transformer. Line 1 and line 2 has an impedance equal to 0.4. So what is required? Determine the swing equation of the machine rotor. Of course, to write the swing equation, it is very simple. How to proceed? If you want to write the swing equation, so can anybody tell us from where we can start? Abdulaziz?
We get the angle of the terminal voltage first.
The angle of terminal voltage. Terminal voltage is here, right? This is the terminal of the machine. So you need the angle here, ولتكن alpha مثلا, for example. So do you know the magnitude of this voltage?
Yes, it's given as 1.05.
Yeah, here, this is a terminal voltage, 1.05. طيب, how to get the angle?
We use the power equation.
BE equal to, between 2 points, you have the voltage here, you have the voltage here, and you know the transfer impedance in between, so you can implement. How much the transfer impedance between the terminal and the infinite bus? So you have here transformer and the 2 lines in parallel. So transformer and 2 lines in parallel, so 0.3 sine alpha. The angle in between is alpha minus 0. So this is equal to 0.8 per unit. So VT is given 1.05, and this is 1. And in this case, you can get alpha. So alpha is 1. Okay, now alpha, we can get it. طيب, if you get alpha, how can you proceed? Ayub, Khalifa?
Calculating the current.
Current. Calculate the current. How to calculate the current?
We have the terminal voltage, we have the voltage at the infinite bus, and we have the equivalent reactance.
Okay.
So
okay. Yeah. Okay, go ahead.
So subtract the terminal voltage from the infinite bus voltage and divide by the reactance.
You will write here what?
V terminal.
V terminal.
Yes, minus the V at the infinite bus.
Over
the total reactance.
How much?
We just calculated 0.3.
هل 0.3 ولا J 0.3?
No, J 0.3.
You have to be careful.
Okay.
This is a phasor VT with angle alpha, and this is one with angle 0. And so you can get the current. And then after the current, you can get E, internal voltage, VT plus I multiplied by JXD prime. So you can get the E prime that we need here, and the angle, of course, which is delta in this case. So you can write now the power equation. So the power equation equal to E prime, which is calculated here, multiplied by V infinity over the total impedance, which is here you have 0.2, 0.1, 0.2, so 0.5 sine delta. So this is the electric power. Once you calculate the electric power, you can write the swing equation. So you can write the swing equation, V square delta by dt square equal to omega s over 2h multiplied by B mechanical, which is constant, minus PE maximum that we calculated here, sine delta. So this is the swing equation. In that case, if we have a fault, we have another swing equation. If the fault is cleared by tripping the line, we have another swing equation. So it depends on the system configuration as far as this reactance will change, transfer reactance. Okay, so we can write the swing equation at the current situation or the pre-fault condition. Now, if a three-phase fault occurs with a fault impedance, so we have here fault impedance of J.1 per unit to the neutral, occurs at point A, low at the bus. Develop the swing equation in that case and find the initial rotor acceleration. Okay, great. So if the fault occurs here at point A, how much the power transfer to the infinite bus here in this case? How much? Is it zero or not zero? Ayub, Rani?
It would not be zero, Doctor.
Why?
Because now the from A to ground is not zero. It's J.1. So there, when we convert from star to delta, so x12 it will have a value.
You are absolutely right. This is a solid fault. If this is a solid fault, then the power transfer equal to zero. But if we have a fault impedance here, in this case, the power transfer is not zero. Okay? You are given here a fault impedance. In this case, there is no power transfer during the fault, although the fault occurs at the bus. But we were talking about solid fault. And you are given here a fault with impedance. So in this case, you have to convert from Y to delta. And you have here, this is combined together. So it is 0.3 reactance here. And at this bus, you have a fault impedance J.1, and these two lines is 0.2 here, J.2 to the infinite bus. So in this case, you need to convert this to delta. So we are interested actually in this impedance only, which is 0.3 plus 0.2 plus 0.3 times 0.2 over the third impedance, which is 0.1. So this gives you 0.5 and this 0.6, 1.1, very well. Keep in your mind when you convert from Y to delta, we expect the impedance to be higher. All right? We expect the impedance of the delta to be greater than the impedances of Y. You can have here, just to check, you may use a different formula from Y to delta or delta to Y, so you can mix. But keep in your mind that Z delta is equal to 3 times if it is a balanced system or balanced load, equal impedances. We expect Z delta equal to 3ZY for balanced system. Usually Z delta is much greater than ZY, just to check. It becomes here 1.1. So this is the transfer impedance during the fault. So in this case, we can write BE equal to E prime constant calculated V infinity over 1.1 sin delta, and we can write the swing equation during the fault. And also, let us see what the switching scenario that we have here. If the fault is cleared in 9 cycles, this 9 cycles corresponding to how long in terms of seconds? Hussein?
9 multiplied by 16.66.
16.67 millisecond, يعني 0.15 second. Okay. 0.15 second. طبعا احنا we based on 60 hertz, يعني this calculation based on 60 hertz. If it is 50 hertz, 50 hertz يبقى one cycle is 20 millisecond. So 9 cycle will be 0.18 second. So in 60 hertz we have 16.67 millisecond for one cycle. So 0.15 second. This is the after 0.15 second from the fault occurrence, we trip the line. The line is tripped. So we need also the swing equation in this case. If the line is tripped, then you have this is 0.3 and this is line is tripped, yani this line is off. Now we have only one line which is 0.4, so 0.4, 0.3, 0.7. So this would be 0.7, and then you can also write the swing equation. So here in this example, we have 3 swing equation. Pre-fault, we have a swing equation. During the fault, this is from t equal to 0 up to 0.15 second, and post fault for t greater than 0.15 second. So we have here 3 swing equations. And we need numerically to solve these swing equations simultaneously. يعني مثلا for example, if we would like to see solve this equations up to t equal to 2 seconds using مثلا Euler method or trapezoidal method or whatever. So what you can do here, you can say no, okay, I will take the time step مثلا delta t equal to 0.0 مثلا for example 1 second. That's for example. So how many iterations do I have? 1 second. We need to simulate the system in order to check its stability up to 1 second. So we can write here 1 over 1. So we will carry out a number of iteration equal to 100 iteration. Okay, great. So the first iteration, which swing equation, we have 3 swing equation here. So for the first iteration now, which swing equation will solve? Abdulaziz?
During the fault?
During the fault. We will solve during the fault up to this time, which is over this. So up to the 15th iteration. Up to 15th iteration, we will solve this swing equation. After the iteration number 16, when the time is greater than this, we will solve this swing equation until the iteration number 100. So in this case, you are going back and forth depending on the switching scenario. Then we may here trip the line, and then the fault doesn't, and then after maybe after 9 cycle more, the circuit breaker closes, the fault is still there, and then in this case we will go from post again during to during, and the circuit breaker opens the line, then we go here, and you need to solve the swing equation according to the switching scenario. Okay, so using the trapezoidal method with a time step of 0.03 second, solve the derived swing equations and study the system stability. 0.03 second here. That means for 0.15 second here over 0.03, it will be 5 iteration. So 5 iteration we will solve during, and after 5 iteration we will switch to post fault swing equation. Is it clear? Any question? If you have any question, please don't hesitate. Okay.
Doctor, why we start with the during fault from the first iteration?
At time 0. This is time 0. And at time 0, okay, at time 0, this is during the pre-fault, right? Our t less than,
right.
let us t less than 0 or equal 0. We have this pre-fault condition. And this pre-fault condition will be used as the initial condition for during fault. And when you go to iteration number 6, and you go to post fault. So the final values here that you calculate in iteration number 5 will be like the initial values for the post fault and so on. So now we are interested in the time t equal to 0 up to t equal to 0.15. So this is during fault, and after 0.15 we have the post fault condition. So when you solve, you solve the during fault. Okay. Of course, the initial value, initial value initial angle, will be calculated from the pre-fault conditions. زي ما حسبناها كده. Pre-fault condition, we have here the BE, we calculate the E and so on, so we can get delta. We have here E is calculated. So E equal to 1.15, for example, with angle 30 degrees. So this is the initial value. This is delta 0. This is delta 0. So or delta of 0. And this is the initial value, where we can start in solving this during swing equation, during the fault. Is it clear?
Yes, it's clear.
Okay. Okay. Ramadan Ali, please go ahead.
Yes, Doctor. Why we will perform 5 iteration during the fault?
لأنه هنا it specifies here the delta t. It gives you delta t here equal to 0.03. Okay, it's given to you, but this is delta t. If you have up to 0.15 second, this is during fault. Am I right? This is during. This is the final time, and this is the step time. So if you divide this time up to this time, low step size, in this case you will find out 5 iteration. So you will carry 5 iteration in this during the fault swing equation. And starting from iteration number 6, you are solving the post fault swing equation. Is it clear?
Yes, clear.
And a number of iteration, this depends on the simulation time, number of iteration equal to simulation time over the step size. So if you select the step size 0.01 second, in this case you will do 15 iteration. Okay. Okay, Hussein Ali, please go ahead, Hussein.
Yes, Doctor. Now, Doctor, here the time step is specified to be 0.03, and based on what we have discussed last lecture, you said that the time step is adjustable, and some time step could lead to converge the whole iteration calculation. So what is the rule of thumb to know we are not in a divergent? We are not toward to diverge. And the second question, why do we choose 1 second? Why not 2 seconds? And what is the limit? What could limit me to use 1 second, or maybe half second or 2 seconds?
Okay. For the first question regarding this delta t, how much you can set? Actually, this is based on your experience with the problem that you have. As we mentioned earlier, it depends on the problem dependent. You may have very slow response system with very slow response. You may have very highly nonlinear system where the disturbance could, have very high frequency, oscillation frequency. Okay, a time step here for this would be different than the time step for this system. For example, in bar system, usually we set delta t very small, and this is a highly nonlinear equation, but this could be 0.001 or 0.005 or 0.01 maximum. Okay, is it clear? Of course,
Yes.
you can start. This one will give you better results than this one, and this one will give you better results than this one. And definitely, as the smaller the step size, the better the solution, or the accurate the solution. Okay?
Yes.
Or
Okay.
more accurate the solution. But you can start with very small value. You can start with very high value. Let us say, if you start with 0.001, if you start with this one, or even if you start with delta t equal to 0.1, for example, and then you will find out that the system diverge. Delta is increasing monotonously. In this case, you don't know whether the system is unstable really, or your step size is very big.
Yeah.
In this case, you need to reduce this delta t, and you carry out the simulation again and see. And but if you start with a very small value, and you find out, this is the delta versus t. This is delta versus t. You will see delta increasing monotonously as such. So in this case, system is unstable. Okay. Is it clear, Hussein?
Yes. Yes.
And you need to select this step size wisely. You can start with very small value, but this will take more time in computation. But you can relax it and see, and so on. But you have to. Yeah. Second one was what is the second question? About what?
Why did you choose 1 second, not half second or 2 second?
1 second or 2 seconds. This is you can you can control it. And just 1 second. This is just for simplicity. إنما the final time it's up to you. You need to check مثلا the swing curve مثلا up to 2 seconds, up to 3 seconds, up to 5 seconds. You can have this also. You can compromise لأنه with the time step you can see how many iterations should I carry out in order to solve the problem. We usually we are very much interested in the first swing. If the system response goes to the maximum and start getting down again, يبقى في أمل في السيستم. there is a hope. لأنه after this is very short. This is very short time. And one cycle after the fault, you can see the response here of the delta reached to the maximum. And then if it starts decreasing, then the controller will respond at that time. So the damping of the other controllers will be active, and this will help in reducing more and more. انما هو the problem is انه this is the first swing, and if the system in the first swing is unstable, and if the first swing is unstable, system goes as such. Okay?
Okay.
Is it clear?
Yes, doctor. I have just
Yeah.
slight.
Okay, go
last
ahead.
lecture you said we have adaptive or a kind of adaptive time step. Is it going to be in the same iteration or the same loop? The time step will it change or maybe increase or decrease, or after the whole iteration or the whole loop it will start again by adjusting itself?
لا within the loop يعني مثلا for example you are solving from t equal to 0 to 5 seconds. This is the final time. Okay?
Yes.
Here طبعا you divide this period to during fault and post fault and so on. So you will see the changes here of delta. During these 5 seconds, you have a loop here. And you have a loop here for calculation. For example, from I equal to 1 up to 5 seconds. لو الدلتا تي مثلا for example 0.01 second, يبقى we will carry out 500 iteration. Am I right?
Yes.
Okay, now if I مثلا just say if I less than, لو احنا خدنا problem اللي هي during والكلام ده، لو لحد 1 second يعني if I less than 100, this is the swing equation that we will solve. Else, this is the swing equation that we will solve. And R. Okay? So this is the for loop here to solve the swing equations. Now, you have here delta of I will be calculated, and you have here delta of I will be calculated based on the second base here of the swing equation. So the code in MATLAB or the function اللي هي ODE code, it has adaptive step size. And this is based on what? Based on the change of delta. When you see here high change in delta, so the step size will be small. But at the end, you can see here, maybe this is from 0 to 3 seconds. After 3 seconds, you experience a slow change in delta. It is not wise to keep the step size very small, although you experience here very slow dynamics. And you can extend the step size based on the difference between delta I and delta I minus 1, for example. Is it clear?
Yes. Restricted.
And you can use some kind of adaptive step size in order to minimize the time of computation. And the idea is to reduce the computational time. إنما طبعا you can keep it running at very small value. It doesn't matter. Okay. طيب. Okay, and I think we already solved the problem. Reactance diagram, you have here this and 0.3, and we get alpha of the terminal voltage, and this is the terminal voltage, and then we have the current, and then we have the E prime. So this is the delta 0 here. This is delta 0 or delta T0 or delta 0. The total reactance, this is this is the post fault. Oh no, this is the pre-fault. Total reactance equal to 0.5. So this is the BE, and this is the swing equation. Okay, this is the swing equation. Omega is equal to 377 radian, and this is 2H. which is given in second. And this is the swing equation. And we can also, for part P, when we have during the fault, so you have here a fault impedance, and to convert Y to delta, so you end up with transfer impedance equal to this. And this is BE, and we can write the swing equation equal to this. This is a constant, omega S over 2H. B mechanical constant, what is change also in only the BE maximum you have here as such. And okay, at the start of the fault, then what it needs some kind of initial acceleration. It was asking about the initial acceleration. Of course, the initial acceleration, this is the acceleration, d square delta by dt, this is the acceleration. So of the angle during the fault, this is the initial angle, and you substitute here this angle during the fault. So this will be sine this, and you can end up with this value. So it gives you, this is the initial acceleration of the machine. So you have here BE pre-fault, and this is during the fault. You were here at the beginning, delta 0, and then you jump to this point. So you are here. So now this is the acceleration power. This is B mechanical, and now during the fault, this becomes B electrical during the fault. So this is the acceleration power, BA. So we can get the acceleration. This is 0.8 minus the value here, which is this value. So you can get the acceleration, the initial acceleration of the machine. The reactance diagram for during fault, post fault, we trip this line. So this is the simply BE, and this is the simply the swing equation in post fault condition. So we have now three swing equation defined as such. For T less than 0, this is the pre-fault, during the fault, and after the fault. Okay, so these are the swing equations. So what is needed? The needed is assuming that the time step is equal to 0.03 second. We need delta t equal to this, then applying the trapezoidal rule to solve this. So as you mentioned here, we will carry out 5 iterations in during fault swing equation, and starting from the 6th upward, we solve the post fault swing equation. So okay, so the time is 0.15 second, lower 9 cycles. So you apply, this is all beta n as defined earlier, and this is alpha n. It depends on the previous values, omega n and BE of n. And this is omega n plus 1, recursive form, and this is delta n plus 1. And this is already shown up before. So what we will do is, let us start with the initial value. Step by step simulation. Initial condition, we have delta 0, and before the fault, the speed of the machine equal to the synchronous equal to 377. You know, this is the initial condition. Everything at steady state, omega equal to 1 or omega equal to omega s. So this is the initial value. So we can calculate now this omega n, which is 377, and then we can approximate the Bn equal to 0.8 initially at steady state, and the delta n at steady state equal to this value. So you can write here Be of 0 equal to this value initially with this, and beta 0 equal to delta 0 plus omega 0, which is, this omega 0 equal to 377. So you can have this. So these are the calculation of beta 0 and alpha 0. Alpha 0 equal to omega 0 plus this value multiplied by E of 0, which gives you this. Okay, now for n equal to 0, we start now, first iteration will end up at 0.03 second. So assume delta doesn't change much. Delta t is small, and this is very important. Then the BE of 1, if you still remember, if you have here any value, let us say any the standard form or the general form, yeah, for this one. For this one, omega n plus 1, you need BEn plus 1. You need BEn plus 1, and the BEn plus 1 will not be calculated until you have delta n plus 1. Okay, and delta n plus 1 depends on omega n plus 1. BEn plus 1 will be approximated to BE of n. Will be approximated to BE of n. And usually the change in the angle is not that much, especially with very small step size here. This is why we need to set the step size very small. So we can approximate Bn of n plus 1 equal to B of n in order to calculate this, and then we can calculate delta n plus 1 and so on. So we can approximate this, and we can write BE of 1 equal to approximately BE of 0, which is this value, and then we can calculate the omega 1, and we can calculate the delta 1, and then we need to calculate here. Khalas, yeah, this is the end of the step number 1. For n equal to 2, we will recalculate alpha 0. Now we calculate alpha 1, and then we calculate beta 1, depends on these values of 1, and then we can calculate omega 2 and delta 2 accordingly. So BE of 2 is approximately equal to BE of 1. Now we have delta 1 is known, so we can approximate for this function 1.001 sine delta 1 now, and this is the power, and we can calculate beta 1, and we can calculate alpha 1, and then we can calculate omega 2 and delta 2, and so on. For n equal to 2 and 3 and so on, and then you can proceed with time 0.09, 0.012, and 0.015. 0.15. Repeat as in previous step. Note at t greater than 0.15, obtain BE from the swing equation of the post fault. So you will get BE from this power angle equation. Previously, we got it from the during fault equation. And previously, we get it from this one. Now we move to the swing equation in post-fault conditions. So this is the way. I think the homework is already. Did we ask you to use MATLAB for solving the swing equations in homework number 3? Did you use ODE or the swing?
No, doctor.
طيب, can you solve the problem or the example? You can solve the example that we solve it now for 1 second. Final time 1 second with a time step equal to 0.001, and you can implement Euler method, trapezoidal method, and Runge-Kutta method, and discuss and compare the results. And of course, you can play with this time step and you can get. And I would like to add here, since we are running the time domain simulation, calculate, take a note, calculate the critical clearing time, CCT. We need to calculate the critical clearing time in this case. Can you calculate the critical clearing time? Can you?
Yeah.
How?
After we replace data M by data max.
Delta M. Where is delta M and delta max? Now we are talking about time domain simulation. And I forget about the equal area criteria now. Even in the equal area criteria, it is very difficult to find the critical clearing time, not critical clearing angle. And here, if you draw the equal area criteria, this is the equal area criteria. And you are here, you move here, and then after some time you go here, and this, of course. Yeah, okay. Of course, if you reach to this value, so you are talking about here delta CC. If this is a deceleration area that you have, where you have here delta M equal to delta max, and this is delta max. Am I right? Salman?
Yes, doctor. Yes.
What you can calculate here is delta CC. Now we need a critical clearing time. How to calculate the critical clearing time here? Can you calculate the critical clearing time here?
We need to integrate.
Integrate what? Yani, here, the only case, let me emphasize on this, the only case in equal area criteria that you can calculate the critical clearing time is where the fault is a solid fault at the bus. So the power during the fault equal to 0. If the power during the fault equal to 0, we can write the d square delta by dt square equal to omega s over 2h multiplied by pm minus 0. And this is constant now. So we can double integrate in order to get the time. And now if we have here during the fault, the power is not 0, it's the function of the angle, V max sine delta. So in this case, we cannot double integrate. We cannot integrate, and we have here sine delta. This becomes very complex. We cannot say this, right? And how to integrate here? Can you integrate here? No, we cannot integrate. So the only case that you can calculate the critical clearing time based on the equal area criteria is where the fault occurs at the bus and the power transfer during the fault equal to 0. Otherwise, we cannot. So let me check Saab كده if he has an idea how to calculate the critical clearing time.
Yes, Doctor. If you're using MATLAB, we can just sweep the time for fault clearance.
You can sweep what?
The time for fault clearance. We can use different times for fault clearance, and we can determine the critical clearing time from that.
Yes, you are absolutely right. You can do this. What you can do is the fault is cleared at 9 cycles or 0.15 seconds. So let me run these codes or one of these codes طبعا يعني doesn't matter. Let me run for 0.2 seconds. The fault is cleared at 0.2 seconds. So if the iteration step equal to this one, this is very small, 0.001 يعني 0.2 second معناها انه 200 iteration. Am I right? 200 iteration ولا 20 iteration؟
200.
200 iteration. So in this for loop that I pointed out before, if I less than 200, then I will use during the fault, else after fault or post fault. And I run. Okay. And at each time, okay, 0.2 seconds, I found the system is stable. When I have delta is increasing and then decreasing again and so on. That's fine. So let me go to 0.25 seconds. Now I will carry out here during the fault 250 iteration. In this case, I will run and see. Probably I will find out the system is unstable. In this case, I will reduce this time to 0.23 مثلا, and then I will run again. So I will carry out here 230 iteration, and then I will carry it again and again, back and forth until I reach to the time, the maximum time that the system is stable under the fault. And if I increase this time little bit, the system becomes unstable. So I can calculate the critical clearing time based on trial and error. I play with the fault time, and then I try as such by trial and error. So this is the only way to calculate the critical clearing time by the time domain simulation. Is it clear? The homework is clear? Take a note here على السلايدز اللي معاك and write, calculate the critical clearing time. Of course, once you calculate the critical clearing time, you can of course get the critical clearing angle. But the critical clearing angle is not that much important for us. Now we need the time duration of the fault. يعني you can calculate, you can add this request here, discuss and calculate the critical clearing time. Of course, you can experience how this time step will affect the solutions and which one gives you the better results and so on. Of course, you can use the MATLAB. You can do whatever. if you can use الماتلاب اللي هو ODE, or you can use also in this هذه سعادات book there is some kind of built-in functions. swing RK4 مثلا رونج كاتا 4 or RK2 اللي هي this or Euler حتى even مثل trapezoidal method. I don't know whether it is there or not. I think it is there. So all these functions are ready, and of course you can go through the textbook and see some examples in order to get familiar with the functions. Is there any question? Yes, Abdulaziz.
We did all this in homework 3. In several examples, we used the Euler method, and we also calculated the critical clearing time by trial.
And I asked you before, and I asked you whether this is included in homework number 3 or not. They said no.
But different, actually, different, doctor. Not same.
They different.
We used the code from the book to it gave us the response, the code for each generator. So we tested with different generators. So,
was for multi-machine.
Yeah, the fault machine. We choose the faulted machine. So the code, it was the code from the book, from the Hadi Sadat book, doctor.
Oh, okay. So
It's the built-in function.
Okay, so you already covered the second part. حتى even we will start with the multi-machine now, and you solve this multi-machine problem, right?
Yes, doctor.
It was multi-machine.
Yeah, it was a multi-machine. We use the code in the book.
Two machines.
Two machines is a multi-machine. And we have
Okay.
single infinite bus.
Okay.
If you have 2 machine or 3 machine or n machine, it becomes a multi-machine bar system. Then the interaction is considered from machine to another. So we have the multi-machine system. So okay. So let us, Ramadan Ali, do you have any question, Ramadan?
Yes, Doctor, about the homework. Do we have to develop our own code, or we can use like built-in functions?
Well, you can do any either. if you have built function خلاص, بس أهم حاجة you know what is going on. You know the idea behind it.
Okay, clear.
You can use the built-in function. We don't want to waste our time for this. Okay. So the second, now we can talk a little bit. This is not the whole multi-machine stability studies that will be covered here. Now we will see the swing equations of the multi-machines and how to solve these in multi-machine context. So the objective of this part is Ayub Wa'il Horani. You have a question?
Excuse me, doctor. For homework, for Euler method, you refer to Euler or modified Euler?
Here I mentioned the Euler method. And now we need to check the extreme cases. Euler, which is the worst one, and Runge-Kutta, which is the best one, or more accurate one, or most accurate one. Okay.
Clear, yes.
And I don't know whether you will do the homework. You know, it was expecting maybe we experienced a delay and or the homework and the lectures becomes unsynchronized. And we have one class where we did this presentations. The presentations covered the whole class and we didn't proceed. So we lost the synchronism. This is why. And I think if you cover this homework that we discussed now, خلاص يبقى no need to do it. And you already experienced how to calculate the critical clearing angle in the homework, right?
Yeah, there were two questions for
خلاص no need to do this. No need. Let's forget about this homework. It was some kind of clarification if it happened before the homework itself. Okay. So in multi-machine, we have some assumptions. We didn't stop for Maghrib prayer, but I think no time is now is plus we have only 3 minutes or something. And then we can steps for multi-machine stability analysis. We will see the steps from where we can start and how to handle different components. We start with the load flow solution, and then we see the loads, how to model them, load modeling or load representation. You can represent the load in different ways. You can have it constant impedance, for example. You can have it constant current load. You can represent the load as frequency dependent. A lot of representation of constant power. A lot of load representations methods that you can use, and this is exactly the case in real life. And maybe some loads can be represented by constant impedance. They have resistance, reactance, and that's all. This is the load. Z load. Whatever the voltage here, it doesn't matter. Whatever the current, whatever the or the voltage here or frequency, it doesn't matter. This is the constant values. Now, constant current, constant power, constant load. If we have this voltage reduced, then the current will increase. Then this load needs constant power. This load needs constant power, be constant. So if we have any change in voltage, this will be reflected in current. For example, some loads are voltage sensitive. If you have a capacitive load or capacitor bank QC, as you have in load flow problem, you use the capacitor bank as injecting the Q, okay? But this is not the case. Actually, if the voltage here changes, then the Q, you have here a capacitor. So capacitance is constant, but the Q equal to V square over XC. So in this case, if the voltage is changing, then Q also is changing. It's not constant. Could be also frequency. Frequency here also this XC equal to 2 by F C1 over 2 by FC. This also frequency dependent and so on. So a lot of ways to model the load. So in stability study, usually we use the constant impedance representation. طيب, let me ask you, and I need an answer. In load flow study, they already use load flow study. In load flow study, how did you represent the load? How did you represent load in load flow study? الحوراني.
Constant power, Doctor.
Constant power.
BQ bus.
Okay. Abdulaziz, do you have any other or the same answer?
I just wanted to get to understand. You mean how to model it in ETAB or just in the load flow?
How to represent it in load flow studies يعني البي ال والكيو ال. هل بتاخدها بي ال وكيو ال ولا بتحولهم لامبيدنسز R and plus GX?
No, we input P and Q.
So constant power.
Yeah.
And طبعا this is constant حتى during the solution. انت during the solution you carry out 3-4 iterations, right? You start flat, V equal to 1. After the first iteration, maybe the voltage V1, V2, V3 equal to 0.99. But you still consider the load is BL and QL. مش كده ولا ايه؟ وفي الايتريشن اللي بعدها الفولتج بتغير ومع ذلك انت بتعتبر ان اللود is constant BL and QL. فده constant power representation. Which is not يعني زي ما قلنا هنا if we have a capacitor والفولتج هنا بيتغير in this case QC is different يعني that's some kind of approximation. So in load flow we represent the load as constant power. In stability study we represent the load as constant impedance. أيوب الحوراني خلاص okay.
Doctor,
yes please.
Why do we need to change, to constant impedance for stability study? For what, what is the main purpose for this change of representing the load?
In order to for analysis purposes, and for analysis of the stability, you need to represent the load, right? And as you can see in single machine infinite bus that we considered so far, during fault, after the fault, pre-fault, and all this will be reflected in X12.
Yeah,
right?
okay, right. Yes, right.
We need an impedance.
Yeah, so we need to figure out the contribution of the load impedance on X12.
Yes. In order to calculate this X12, the transfer impedance between the generators, in this case, you need to represent the load, to take the load into consideration here. This will be reflected here as impedance. Okay? طبعا, of course, we need some kind of system reduction. We will see how to implement it later on. And we can develop the swing equation of each machine, and then we solve them simultaneously. I think time is over, and we have to stop here. So if you have any question, please continue. Otherwise, you can leave. And as we agreed on,